Okay, so section 5.7 talks about the cross product. It's an amazing calculation that gives you some really cool stuff. The cross product of two vectors is going to give you something that's perpendicular to both of those. So for instance, if I add vector v here and vector w here, pointing that way, then the cross product is going to be something that's perpendicular to both of those. It's going to be perpendicular to v, it's going to be perpendicular to w, and I can't draw that really well, but it's going to be perpendicular to both of them. So how do you calculate that? You're going to calculate that with a determinant. Now my I, j, and k here are not just letters. They're actually unit vectors themselves. These are the familiar ones that you have throughout chapter 5. 0, 1, 0, 0, 0, 1. But we're not going to use it like this until we're all done. So the cross product starts out with the top row of a determinant as my I, j, and k. I, j, and k. And then the first vector is this one, 1, negative 3, and 2. The second vector is this one, 2, negative 2, and I think that's negative 1. Let me just double check here. Yes, negative 1. So negative 1. Now this is just calculating a determinant, although the constituents of the determinant are a little different than what we're used to. We're going to start with the I and do what's called cofactor expansion. It's going to be I times the matrix that I get when I cross off this row and this column, or the determinant of that matrix. So that's going to leave behind negative 3, 2, negative 2, negative 1. Negative 3, 2, negative 2, and negative 1. So there we go. We got the I part. Cross off this row and this column. For the J part, we're going to do similar. J, and cross off the top row and the middle column, leaving behind 1, 2, 2, negative 1. And last but not least, the K, cross off the top row, and the third column is going to be K times 1, negative 3, 2, negative 2. The one thing that I haven't told you is how to combine these things yet. And it always follows the same pattern, plus, minus, plus. So plus, minus, plus. That's what goes between them. And really all that it amounts to is a fancy way of remembering that the middle term is going to be negative there. This is going to be I. And since this is a 2 by 2 determinant, it's going to be the product going down. Negative 3 times negative 1 is positive 3, minus. And write that minus before you do your calculation of the product going up. Product going up is negative 2 times 2, which is negative 4. So you got a double negative there. That's okay. Again, for your determinants, it's the product going down. 1 times negative 1 is negative 1, minus the product going up. And last but not least, there's K times the product going down, which is negative 2, minus. And again, write that minus before you work on the product going up. Because the product going up gives you a negative 6. So again, you've got a double negative. That double negative here gives me a total of 7I minus j times negative 5 is a plus 5j. And then negative 2 plus 6 is positive 4, positive 4k. Now, what's amazing is that this vector should be perpendicular to both of these vectors. How do you determine that, or how could you show that this vector is perpendicular to these two? Let's call this vector z just out of convenience. Can anyone tell me how I could show that two vectors are perpendicular?
Multiply it, it should be 0.
Yeah, good. The dot product should be 0. So I've got z equals 7, 5, and 4, and v equals 1, -3, and 2. If I did the dot product of z dot v, it'd be 7 times 1, which is 7, plus 5 times -3, which is -15, plus 4 times 2, which is 8, and that gives me 0. Beautiful. Likewise, if I did z times w, 2, -2, -1, so 7, 5, and 4. So let's see, 7 times 2, z dot w, 7 times 2 would be 14, plus -10, plus -4, and again, I get 0. So this vector is perpendicular to both of my original vectors. Now there's a different fancy way to say that, and you've already learned one way. It's orthogonal to these vectors. But I'm going to add to that one more. This vector is normal to those vectors. So perpendicular is equivalent to orthogonal is equivalent to normal. And there are actual nuances here, but for the purposes in our class, they're mostly interchangeable, all right? Normal is just kind of a fancy way of saying perpendicular. Our new
Wait, when would it equal parallel then? When it equals 1?
Yeah, so it'd be parallel if the dot product, well, it's a little bit more than that. To decide if they're parallel, then this calculation, cosine of theta equals u dot v over length of u times the length of v. That would have to be, actually, let's think here. It'd have to be 1. Yes. And then the angle between them would be 0. Or -1. Making me think about it. Because then that would be 180 degrees, but then it would still be considered parallel. So if it's 1 or -1, then it'd be parallel. U and V are parallel. Yeah, because if it's 0, then cosine of theta equals 0. That is, if the dot product is 0, cosine of theta equals 0, then theta is pi over 2. It's the inverse cosine of 0, which is a 90-degree angle, so perpendicular. All right, there's more that we can get out of this. We're going to get a lot more out of this with like almost no work. So just a moment ago, I calculated V cross W, and I got 7i plus 5j plus 4k. If I did W cross V, I don't have to redo this calculation. What happens is it changes all these signs. I get -7i minus 5j plus, or excuse me, minus 4k. It's just going to completely switch all the signs on these terms. And that's the only change you have to make. So there's no new work to do. That's the important thing. Now, that actually leads to the answer of one of your questions. So here's one of your homework questions. If you did U cross V, then V cross U, is that equal to 0? True or false? What do you think?
True.
True.
Yeah, you can see it here with this example. If I were to add these two things together, then on the right-hand side, I would get 0 plus 0j plus 0k.
What? I'm
That
so
would be
Oh, that's not much to say.
V
No,
cross
I
W
don't know.
plus,
What you talking about? Me?
Kayla, if you could mute yourself, that'd be great. Let's see. So V cross W plus W cross V is 0. Nice. All right. Now there's some more we can get out of this example as well. If you did V cross itself or W cross itself, and I'm not going to go through the calculations, but V cross itself would be 0, 0, 0. Same with W cross itself. When you cross a vector with itself, you're going to get a 0 vector, which I never liked that terminology. The 0 vector always bothered me. It still does. Now, I'm not going to take the time to do it down here, but it says find a unit normal vector to the plane containing this. Let's apply this question to these numbers. If I wanted to find a unit normal vector to the plane that contains, say, V and W, then what I have to do is I have to take my result of V cross W and just make it a unit length. So let's do that. So find a unit normal to the plane containing V and W. Note, just make vector Z a unit vector. So all we're going to do is we're going to take our result from V cross W and make it a unit vector. So that vector I called Z just out of convenience. And remind you, Z was 7, 5, and 4. If I want to find a unit vector, then I got to figure out its length. What's its magnitude? So the length of Z is going to be the square root of 7 squared plus 5 squared plus 4 squared. So 49 plus 41. So what, 90 square root of 90? Or 3 square roots of 10. I just want to double check myself real quick here. 49 plus 25 plus 16. Yeah. Square root of 90. You know what? We're just going to leave it square root of 90. I'm not going to fuss with the 3 square roots of 10. If I want a unit vector is going to be 1 over the length of Z times Z. Or in other words, 1 over the square root of 90 times 7, 4, 5. Or 5, 4. And that's my unit vector. So they're asking you to take the cross product and then find a unit vector. Is all they're doing there. Anything on that one? I'm just going to make one last comment on a couple problems and then we'll call it a day. Nothing there. Example D is a good one.
Actually, a little bit with the ending part. I was a little confused with the U equals part. I can get all the way up to.
Okay. So you got square root of 90?
Right.
So we're creating a unit vector. So to create a unit vector, all you're going to do is you're going to take and multiply a vector by some number to shrink it down to have unit length. So you're basically dividing it by its length. Let me see if I still
I think,
have this one up here. So for instance, the vector here that I've got 2, -1 right there, that's a vector of length square root of 5. If I want to take that vector and shrink it down to something of unit length, then I'll take that vector and divide it by the square root of 5. And that's going to shrink it down so that it's on this purple circle, which is everything of length 1. So if you take these two numbers, and can you follow me that the length of this vector is 5, square root of 2 squared plus -1 squared? 2 squared is 4 plus 1 is 5. So the length of this vector is the square root of 5. If I wanted a unit vector, then I would just take each of those terms and divide it by the square root of 5. So let me just show you that real quick. 2, -1. That's my vector. Call it V. My unit vector is going to be 1 over the length of V times 2, -1, which is 1 over the square root of 5 times 2, -1, like that. Or you could write it as 2 over the square root of 5 or -1 over the square root of 5.
oh, I see it now. Okay.
Those both have a unit length, and you can check it. If you check the length of U, it'd be the square root of 2 over square root of 5 squared plus -1 over square root of 5 squared. That would give me 4/5 plus 1/5. Add them together, I get the square root of 1. So it has unit length.
Oh, okay. Yep, I see it now.
Same thing's happening here. No, I appreciate the question. Thank you.
So either form would work, right? I could do like the 1 over square root of 5 and all that, and then they'd both be correct?
Yeah. So,
Okay.
so this or this, both of them are equivalent. You might want to
Okay.
take care with what they're asking on my math lab. All right.
Thank
I
you.
didn't want to do any more calculation, and I won't. Remember, when you do a cross product of two things here, U cross V, you get something that's perpendicular to both of them, right? So I'm going to get a vector that's perpendicular to U and V. Here's the thing. If I then do the dot product of U and something perpendicular to U, the dot product of U and something perpendicular to U is going to be what? 0. Because when I do this calculation in yellow, I'm going to get something that's perpendicular to U and perpendicular to V. But most importantly, it's perpendicular to U. So if I take the dot product, I'm going to get 0. So the answer would just be 0 right here. It's not going to work out to 0 here because you got 3 different vectors. But up here, it is 0. And I could show that to you, but we're already over time. So okay. I think we'll stop it here.